The large language models of today have dimensions in the high 4 or low 5 digits. But you could imagine a model like ChatGPT or Claude having to represent millions or tens of millions, if not billions of features across all of language and reasoning. How do they do this? The story of the answer starts in 2020. Researchers from OpenAI zoomed in on a neural network. Similar to the way microscopes led to cellular biology, focusing on individual neurons and so-called circuits of neurons led to a better understanding of the world that goes on inside a neural network. The paper talks a lot about features, which are either low or high-level tasks that a neuron accomplishes. An example would be a curve detector at a lower level, or perhaps an ear detector at a higher level. It's interesting to see the neurons which cleanly describe a feature. For example, the one they describe that detects dog heads. This neuron looks, as you might expect, like a super-duper trippy dog. Though those are cool, perhaps what's even cooler is the neurons that seem to do multiple different things. For example, this is one that activates when it detects faces of cats, cars, and legs of cats. This neuron would then be part of many different circuits that would later detect larger sets of cats and cars and maybe even higher level things. What's also important is that this neuron is not detecting some weird average of like cat features and car features. Rather, it's explicitly searching for cat-like features, whiskers, and car hoods. These types of neurons are called polysemantic because they represent many things at the same time. This, of course, begs the question of what the hell is going on here? One hypothesis for why polysemanticity occurs is called superposition. It's important to note that this hypothesis isn't really proved, as talked about extensively in this post that I'll link in the description. The first thing to accept in this hypothesis is that ideally, models represent features as vectors that are perfectly perpendicular to one another. This is still a bit up for debate, but it hopefully makes some intuitive sense, as when vectors are perpendicular to each other, there is no overlap between different vectors, and thus different features. As an example to illustrate this, imagine you were a model that had to classify images into either it being a dog or it being a cat. If you decided to have some feature of catness, whatever that means, lying along the x-axis, your representation for dogness should probably be on the y-axis. If your dog vector was instead super close to the cat vector, they're basically pointing in the same direction and thus very difficult to separate. And in this case, we say that the dog vector feature interferes with the cat feature. In the extreme, they are both the same vector, and there's complete interference. So perpendicularity is what we want, because that's when there's absolutely no interference. So here's a simple but related question. What's the maximum number of vectors you can put in 2D space such that all the vectors you choose are all perpendicular to one another? Well, it's 2, the x-axis and the y-axis, as we just went through. How about 3D space? Well, you have the x-axis, the y-axis, but now also the z-axis. So there are in fact a max of 3 perpendicular vectors, and thus 3 features we can cleanly fit. This is, in fact, true in complete generality. Any space, n-dimensional space, has a max of n mutually perpendicular vectors that you can fit in it, and thus n features. And since if you look at a layer of neurons in a neural network, each neuron can be thought of as its own dimension, and you can check out our previous video if you want an intuition of why this is true. Since each neuron can be thought of as its own dimension, this means you can represent as many features as there are neurons in a layer. And this would mean that each individual neuron gets its own individual feature lying along its own axis. But then you might be asking, why did that neuron have to represent car hoods and cat ears and also whiskers? Isn't that just an awful representation? Well, maybe not. Turns out you can represent way more than n features in n number of neurons. Like, a lot more. Exponentially more, in fact. I didn't lie to you, though. The number of perpendicular vectors in n dimensions is, in fact, n. So how do models do this? they represent features instead of completely perpendicularly as almost perpendicular. So there's interference, but very little. And the number of almost perpendicular vectors grows very, very quickly. There's a theorem in math that states that the number of almost perpendicular vectors in n dimensions grows exponentially as n increases. Two vectors, u and v, are said to be almost perpendicular if their dot product, which is basically just a measure of direction similarity, is less than a certain small error term epsilon. If we look at this histogram of the distribution of dot products in different dimensions, we can see that at higher dimensions, the dot products of randomly chosen vectors are more centered around 0, which means they're closer to being perpendicular. And this next line chart shows that in higher dimensions, the number of vectors that we're able to fit with an error term is growing exponentially as the dimension increases, not linearly. This shows that at higher dimensions, if you're just a little bit lax about it, you can fit an insane number of almost perpendicular vectors into it. So models have learned to pack multiple numbers of features into each neuron by arranging the features to be slightly off of perpendicularity. There's another important factor in superposition: sparsity. You can kind of think of sparsity as the rarity for any given feature to show up. At high sparsities, a given feature rarely shows up, and at lower sparsities, the feature shows up more and more often. So at higher sparsities, the interference that features have by not being completely perpendicular to each other usually doesn't matter too much. Anthropic, in 2022, studied this in their article called Toy Models of Superposition, which explores this idea a little more. In this picture, they look at a 2D space that has to represent 5 concepts with different levels of sparsity. If there's no sparsity, that means that all of the features are present all of the time. In this case, you'd want to choose to represent the 2 most important features, as otherwise you'd get constant interference if you tried to represent more and they were to always show up. But at higher and higher levels of sparsity, more of the features are represented by the model, as it can now tolerate a little bit of interference between the features because they aren't being concurrently activated as often. An example we found of superposition in large models is in text embeddings. For those of you unfamiliar, models have learned how to project words into a super high dimension to encode some semantic meaning in its dimension. A common example given for this is that the vector embedding for king minus the vector embedding for queen plus the embedding for girl is roughly similar to the vector embedding for boy. So this king-queen direction vector could represent something of a gender feature. The dimensionality of even the biggest embedding models today is something like a few thousand, but you can imagine there being so many more features that a model has to learn to represent than a few thousand. In fact, superposition is saying that a smaller model is just approximating a larger one. If a larger model could cleanly represent 100,000 features in 100,000 dimensions, a smaller one might noisily put that into only 1,000 dimensions instead of 100,000. There is some noise, of course, but in a way, a smaller model using superposition is mathematically equivalent to noisily approximating a larger model. Also in Anthropic's article, they say there are 3 possible options for what happens to a feature when it is learned by a model. Either the feature just may not have been learned, or it may have been learned in its own dimension, or it may be demonstrated in superposition. And what they noticed is that the transition between these states resembles a phase change. They trained a toy model to represent 2 features, but only gave it 1 dimension to work with. So basically the simplest test of superposition you could come up with. 1 dimension can be represented with just a line, So there is only one possible vector you could come up with that is perpendicular to everything else. They fixed the first feature at an importance of 1, which doesn't really actually mean anything unless you compare it to the importance of the second feature, which they varied between 0.1 and 10. Basically, the second feature varied from a tenth as important as the first to 10 times more important than the first. They also varied the sparsities between 0, which means both features always show up, and 1, which means neither of the features ever show up. So what exactly can the model do in this situation? There are, the authors note, 3 ways to store 2 features in one dimension. Either represent only the first feature and discard the second one, which would be 1, 0. You could also do the opposite, representing the second feature and discarding the first, which would be 0, 1. Or you could represent both in superposition, which would be 1, 1. In this case, you lose the ability to represent both simultaneously, as if you wanted to plug in both being active, the vectors would destructively interfere into 0, representing nothing. So let's try thinking about this intuitively for a bit. What would we expect? Let's draw a graph for the 2 variables being changed here, importance and sparsity. When the sparsity is low, the 2 features often show up together. As an example, when sparsity is 0.01, the probability of an individual feature showing up is very high, at 99%. And the probability that both features show up together is 99% squared, which is 98.01% of the time, which is very often. What would the model do when both features show up often? Well, it would prioritize the one that's more important, as otherwise it would get a worse result when both features show up. So at low sparsities, you could imagine that when the second feature has an importance of less than 1.0, the model represents only the first feature, with 1, 0 as its weights. And when the second feature has an importance of greater than 1.0, it would choose to represent the second feature only, with 0, 1 as its weights. And if you look at high sparsities, the model often doesn't run into collision between features. This, as we discussed previously, is a perfect time to employ superposition, which would be the weights 1, 1. Really no matter what the relative importance is, as now the determining factor is just the extremely high sparsity of the features. Now, if you look at when the features are of the same importance at 1.0, you could imagine there's a feature sparsity at which it just becomes more effective to just choose one at random and represent that one feature instead of happening to represent both, which would fail when both features are active together, which happens more often at lower sparsities. Maybe that point is somewhere here, and when the second feature is less important, the same point still exists, but probably at higher sparsities, because now the model is only willing to represent the second feature if the sparsity is high enough to outweigh the cost of representing that less important second feature. The same goes in the opposite direction when feature 2 is 10 times more important than feature 1. And by this reasoning, you can imagine there being something of a line between these points, which segments this diagram into 3 regions with the 3 possibilities of what the neural network could do at different importances and sparsities. If you've taken chemistry or physics, you might be noting the resemblance of this to a phase diagram. This is the phase diagram of water at varying pressures and temperatures. And you could say that this is the phase diagram of this neural network, with sudden changes of the weight representations akin to the way water suddenly boils at 373.15 Kelvin at room pressure. And when you actually train a network to do this, as Anthropic did, this is what they observed. It looks flipped because the paper used 1 minus sparsity as the y-axis instead of sparsity itself, but let's just flip it real quick, and we get this. This is actually insane. You can actually model the phase change that our neural network, albeit a very, very simple one, is going through. This is an example of studying a network to see what it's learning, and a strong example of superposition in a real model. This is also an example of predicting the way a neural network behaves, which is a frontier that we've really yet to explore. There are so many cool things that networks do that we haven't even begun to touch on in this video. The reason we care about this stuff, by the way, is because of the emerging field of mechanistic interpretability. It focuses on how neural networks learn what they do, and use the things that they do end up learning in order to achieve a task. Polysemanticity, which is the discovery that individual neurons represent many different semantic meanings, as well as phase changes, were found this way. And it's led to a lot of our modern, albeit quite limited, research into deep learning. Using the tools from mechanistic interpretability, we found circuits that do different things. An example of a monosemantic circuit, i.e. representing one feature, is the circuit for the Golden Gate Bridge in Claude, which led to the somewhat incredible demo of Claude thinking it was the Golden Gate Bridge in every conversation and steering every conversation in that direction. Polysemanticity, as you would expect, makes mechanistic interpretability very difficult. Instead of circuits having clean mappings, they activate for incredibly various things that we don't even particularly understand. As Chris Olah, one of the writers of both the OpenAI and Anthropic's articles I mentioned today, has said, neural networks are grown, not made, and we're still a very far away from understanding them.